Hi, I am Amin Gafil, and these are my group members, Sidrashul Muntaha and Tuhab. Concerning the video of presentation, we will see nine sections, which are target application, choose selected and justification, SAST, same grep, setup and execution, finding and result of same grep, and ZAP setup and execution, finding and result of the task, ZAP, Trivy, tool setup and execution, and finding and result of Trivy, and finally comparative analysis. Beginning with the target application, we chose the OWASP juice shop as shown in this figure because of four reasons. The first reason is that the application is legally permitted and locally deployed with no real systems targeted, and it is specifically built for testing the vulnerabilities inside the web application, and it is maintained by OWASP, which means that the found vulnerabilities are directly mapped to OWASP job chain, which uses the work as a security engineer. This application, which means the Juice Shop application, was built using the Node JavaScript and Angular language.
In this section, I will explain the three selected tools and the reason for choosing each one. For the tool selection, each tool was chosen for a specific reason. SEMGraph was selected as the SAST tool because it can analyze the source code directly without running the application. This makes it useful for finding insecure coding patterns before deployment. OWASP ZAP was selected as the DAST tool because it can test the running Juice Shop application from an external user perspective. It is suitable for detecting running time issues such as circle injection, redirects, missing security headers, course misconfiguration, and error disclosure. Chewy was selected as the SCA tool because it can scan dependencies, packages, and container components. This is useful because modern web applications often rely on third-party libraries, and some of these libraries may contain known vulnerability. So these tools were not selected for the same purpose. Each one was chosen because it supports a different part of the security testing process.
Then next, we move to same grep setup and execution. Concerning the same grep installation and configuration, the latest same grep version is installed in this experiment is 1.168.0, and this is the latest version of SameGrep, and it is installed in Ubuntu Linux with the aid of Python virtual environment to isolate the environment. Based on the experiment, the installation consists of four steps, which are confirmation. The first step is the confirmation of installation of Python in the Ubuntu, and then creating a virtual environment to isolate the environment, and installation of the third one is installation of SameGrep tool, and then verification of Dutch installation of this tool. And for the rule pack here in this table, We use three role configuration. The first one is for security rules. The second one is for general security coverage, and the third one is for direct WASP job mapping. Then for this SAS execution methodology, there are five steps to be executed in order or consequently. The first step here is to reactivate the virtual environment before doing any testing or scanning to isolate the environment. The second step is to go to the folder and pinpoint to that folder which was cloned from the GitHub, which is the Juice Shop folder. The third step is to launch the scan with the rules stated, the three rules stated before in the table. And the fourth step is to save the result into a new file uh, to not to lose the result. Finally, the step 5 is confirming that the output file is already saved in the workspace environment and after scanning. And each step has its own command lines as shown here in this page. So moving to the finding and the result of the same group 2. So after a scan of less than 2 minutes, we got 1002 files scanned and 149 rules applied. 19 vulnerabilities from 38 were application source code, while the others were for the infrastructure vulnerabilities. CI/CD. And this in this table, the top most critical findings are fall into three categories. In top 10 WASP, which are E05 injection, E03 cryptographic failures, and E01 broken access control. So in the result, we got four true positives mentioned in the green color, and one false positive mentioned in the red color, which means four true vulnerabilities are correctly classified or detected, while the one normal code was incorrectly detected as malicious code. These statistics gives us a prediction rate of 80%. Then finally, concerning the coverage assessment, the tool missed two important vulnerabilities in the code, which was business logic flows involving manipulation of the checkout process, such as applying discount codes repeatedly and adjusting basket quantities, and missing the other false negative detected is missing authentication on protected routes, uh, which means the juice shop's administration route is accessible without proper authentication.
Hi everyone, my name is Du Hao, and my student ID is MEC251008. In this part, I will present the DAST section of our project. I used the OWASP app to test the locally deployed OWASP Juice Shop application. This section is about the setup and execution of the DAST scan. For the DST tool, I use the OWASP app version 2.17.0. Before scanning, I installed the Java runtime and make sure OWASP Juice Shop was running locally in Docker. The target URL was HTTP localhost 3000. After that, I opened the OWASP app in standard mode and selected automated scan. I set the target URL to the local juice shop address. I also enabled traditional SPAD and AJAX SPAD with Charamo. After the scan was completed, I explored the HTML report for later analysis. The next part shows the findings and results from the ZAP scan. The ZAP scan found 15 alert types in total. This included 3 high-risk findings, 5 medium-risk findings, 4 low-risk findings, and 2 informational findings. The main findings were SQL injection, internal and offsite redirect, missing content security policy, cross-domain misconfiguration, application error disclosure, and section ID in URL rewrite. These findings shows that ZAP was useful for finding runtime issues in the running web application. For the false positive analysis, I manually checked the 5 selected findings. I reviewed the request, response, state code, handlers, and evidence in the ZAP report. Among these findings, 4 were true positives. One finding private IP disclosure was context limited because it came from the local Docker environment. ZAP also had some limitations. It may miss access control or IDOR issues if login rules are not tested. It may also miss stored XSS and business logic problems because these often need manually steps. Also, ZAP cannot inspect source code or dependencies. Overall, OWASP ZAP was useful for testing the running web application, but it should be used together with SAST and SCA for better security coverage.
Hello and Assalamu alaikum. This is Sidratul Muntaha, and I will be walking you through of our software composition analysis tool Trivy and how we basically integrate this to our available application for us Juice Box. So before we see how this Trivy actually works, let us go through the installation and setup first. So Trivy was installed in our Kali Linux CLI using a virtual machine with custom setup, and the installation steps will be as follows. Since Trivy is something that is run on the cloud, we first need to set up Docker, the latest version of Docker, so that we can pull Trivy and our vulnerable application via Docker and use it from our CLI panel. After setting up Docker, we need to pull our target asset, which is JuiceShop, and then we need to install our Trivy engine. Since we will be using the CLI panel, we will use the Trivy from GitHub rather than using from directly their source. And after installing Trivy, we will clone the actual GitHub repository of JuiceShop so that we can get a better result and we can get all the necessary files for our scanning. Okay, now that we have set up the whole environment for using Trivy, the actual process of scanning vulnerable files or composition are as follows. So since Trivy uses the scan results against existing database in its memory, so the first thing we need to do is update Trivy database so that all the latest vulnerable enumeration are stored in its memory. So after updating the database, we go to the JuiceShop directory from our CLI panel, and then we run our first scan on the file system named packagelog.json, So we'll be doing two scans, one on the file system scan and another one is the disk image scan, which is stored in a Docker file. So after running our first scan on the file system, we save the output as .txt, and then we'll do our second disk image scan, and we'll be saving that output in text format as well. So after the two scannings are done, which will take around at best 1 minute, and we'll be confirming whether or not the files are actually there via the command ls, which shows all the files in the directory. Now that we are done with the installation, setup, and scanning the vulnerable files, now we'll be going through our findings and results. What we did find after scanning our vulnerable files. So, as previously mentioned during the execution methods, the TPA actually scans two types of files. The one is the file system scan, which scans for dependencies. Another one is image scan, which basically scans for operating system level files. So if we look at the findings from two perspectives, we can see that the file system scan scans for source code, and the file is package.json, and the image scan actually scans for Docker images that is already embedded in the files that are in the repository. The scope of file system scan is that it scans application layer npm dependencies only, but the image scan it scans operating system level packages plus application npm dependencies. If we see at the findings of the scans, the total vulnerabilities that was found in root package.json, which is the main file, was if we filter it by high and critical, there was 40 high and critical level vulnerability in file system scan, but the total scan was 67. The rest of the severity was below critical or high, and in image scan there was also 67 vulnerabilities. And in front end, the file system scan actually found a total of 17 vulnerabilities, among which 7 were high and critical. For the image scan, the result was also same. So the operating system level finding is that in file system scan, there is no OS level scan, but in image scan, they actually found 12 vulnerabilities in different libraries. The severity range in file system scan is that it starts from low and ends in critical. The same goes for the image scan. And if we look at some of the highest severity examples in file system, the one of the example was the crypto JavaScript, which is related to cryptography and which is very critical, which basically leaks the data and the key. Then the second one is the socket IO parser, which is high, and the last one would be the JSON web token, critical. So crypto and JSON web token, these two are critical. In image scan, there are some app layer common vulnerability evaluations and some libraries such as G library C or Z library, which are medium category severity. The scan also found some secret vulnerabilities as well. In file system, there was a build library, insecurity.javascript, and another one is the library of insecurity.ts. And in image scan, there was actually no secret scan reported separately. So if we look at the unique points of these two scannings, the first file system actually confirms vulnerabilities present in source dependency tree, which is useful for deployment testing. And the image scan, it actually confirms the shift in the deployed container or Dockers, including the inherited operating system risk, which actually can be tested during the live sessions. And if we see at the if we look at the key takeaway from these two scans, the file system scan tells us that vulnerabilities exist at the port or dependency level, regardless of their build. And the image scan tells us that the container adds additional operating system level attack surface not visible from just source code alone. So in brief, these are the findings from our two scans. To determine the accuracy of our scan, we have randomly tested 5 samples for false positive analysis. And if we look at the package or installed version here, all of these five were actually marked as critical. So the first one is the JSON Web Token version 01.0, which is a true positive. The second one is Crypto JavaScript version 3.3, which is also true positive. And all of these were actually verified against the GitHub Security Advisory. The third one we took is the Express JSON Web Token, which is also a true positive. The third one is Elliptic, which is an elliptic of cryptography related with data encryption. So it was marked as true positive, but it has some severity discrepancy, whether or not it should be considered as a high level severity or low level severity. So for now, for this scan, we can consider it as a true positive. And last one is the sanitized HTML, which is basically represents whether or not the HTML fields are sanitized or not. If it is not, then those are prone to vulnerability, which is also true positive. So considering that all the five samples have been manually tested and found that all these are true positive, it can be said that the accuracy of this scan is quite good because there was actually no false positive. So maybe if increasing the sample size, we can actually further determine whether or not these accuracy are present or not. Of course, just using five samples does not actually tell us whether or not this tool is omnipotent or not, because this tool also has some limitations. If we look at the identified two false negatives here, the first false negative that Trivy actually failed to identify is the SQL injection. It cannot even trace the basic SQL attack like the one that is mentioned here, because this is not actually a vulnerability. This is rather than a developer's choice of coding, how he actually coded the whole application and how it was tested against quality assurance. So, and also the source code that are present in the Choose Shops repository, there is no specific CVE code for those codes, because it is something that was made intentionally vulnerable. So for this reason, Trivy cannot actually find this vulnerability. The second is the broken access control. So the broken access control is not exactly you could say a vulnerability, rather it's a let's say it's a rather it's a defective business logic flow in authorization. So in order to identify the broken access control, TV actually needs to know the semantics of the business or know about the access control, which is not actually possible. So because of that, we cannot actually identify the broken access control vulnerabilities, which can be actually found through static or dynamic analysis. We have seen so far three different tools used in three different categories in static analysis, dynamic analysis, and software composition analysis. So in the next slide, we will be briefly reviewing the different scopes and the comparison in terms of different dimensions. So the first one is Trivy, which is a software composition analysis tool. The second one is the SimGraph, which is a static analysis application security tool. And the last one is the ZAP, which is a dynamic application security tool, which scans running application via the HTTP traffic. So the first one actually detects the known common vulnerability innovations in third-party libraries, operating system packages, and functional layers. The SameGraph, it detects custom code flaws, physical logics, hard code, and secrets, which is basically a static analysis without running the actual application. And the third one actually runs the application and finds different vulnerabilities such as the cross-site scripting or the SQL injection, broken authentication, etc. In terms of vulnerability accuracy, the Trivy is high for known catalog CVEs that are present in previous database, low false positive rate on established libraries, as we have seen in our previous presentation. The SameGraph has moderate to high accuracy depending on the heavily on the rule quality, the rules that you have set. The more the rules are better, the more better result it will give you. The SAP is actually moderate, effective at confirming exploitable runtime issues, but can miss logic flaws and produce false positives from generic scanning heuristics such as the authentication dependent pages. If we talk about the coverage, 3B has a broad coverage for supply chain risk because it can scan NPM dependencies, operating system packages, ISC, etc., but blind to custom application logic and updated vulnerabilities such as zero-days vulnerabilities. The SameGraph, on the other hand, is broad for code level issues, authentication logic, injection points, secrets, but limited to what's expressed in source code, not runtime behavior. And the ZAP is actually broad for externally observable or runtime issues, but limited by crawl depth and authentication complexity and can't see the internal code logic. And if we talk about the use of uses, TB is the most easy to use because it can be used from CLI. You don't have to download anything from servers, and it has a basic minimal configuration. You can also run it in virtual machines. The SameWeb is also easy to run out of the box with default rules, but writing custom rules can require an extensive knowledge of application security. The ZAP is actually heavy to run. It requires configuration, target scope, authentication, and let's say environment setup. And the graphical interface also helps, but setup is definitely heavier on the laptop. So if we talk about the best fit, Trivy is actually a best fit for early build stage or pre-deployment sessions. SameGraph is actually best for development stage or to catch insecure coding patterns during or before the code review. And the ZAP is actually useful when you will be testing it on live in your local host or during the quality assurance test. So that's actually all from us. Thank you for listening.